This is not where I wanted to be. I wanted to start here. All right, so suppose we have a car that is traveling at a variable rate from t equals 0 to t equals 2 hours. Here's the graph. We want to know how far the car traveled during those 2 hours. How far did the car travel? Ah, yes, wonderful, Derek. The area under the curve, exactly. So the area under the curve would be how far this car traveled. And that would be really easy to figure out if it was like a nice horizontal line or even just like a straight linear function. But sometimes we have these functions that are not as easy to deal with, like these weird looking curves. And so we have to figure out what the area underneath this curve is. And before we can do that using an integral, because I'm sure that you all know that that's how we should do that, we also have to talk about some of the ways that we can approximate the area underneath the curve, because that's still something that they might ask you about on the AP test. So there are a lot of ways we can approximate that area underneath the curve. There are about 5 good ways that we can, well, 5 mediocre ways that we can approximate the area underneath that curve. And we're going to talk about 4 of those ways today. So the first of those is what we call a left rectangular approximation. And so hopefully you have seen this before because you were in my class, or if you haven't seen it before because you weren't in my class last year, it's pretty easy. So all you do is divide your interval. So we've got an interval from 0 to 2 into as many different little subintervals as you want, and take each of the little subintervals, and at the left endpoint of each of those subintervals, draw a straight horizontal line and then a straight vertical line. Pretend that's what I drew. And make a rectangle. And then it's very easy to find the area of that rectangle, assuming you have the value at the beginning of that interval. And then you do the same thing again for the next little subinterval, and then you do the next thing again for the next subinterval, and again for the next, that one didn't come out very well, the next subinterval, and again, and again, and again, and again. And then you just add up all of those, and that's a left rectangular approximation. Sometimes we call this a left Riemann sum. And a couple things that we will note. First off, that when the function is increasing, so if f is increasing, what does that tell us about the approximation?
Underestimate.
It's an underestimate, and if the function is decreasing, it tells us that this is an overestimate. Good or no? Yeah, no, maybe.
Splendid.
Great. All right. So that's the left rectangular approximation, but note that the larger the subintervals, the less accurate our approximation is. The more subintervals we have, the better our approximation should be. Yeah? All right. Well, we've got a left rectangular approximation. It seems like it's only reasonable that there be a right rectangular approximation as well. So for this one, we do the same thing, except we start at the right endpoints of each of our subintervals, and we make a bunch of rectangles. Just like that. And very similar to the left one, it's not the best method that we can use. Sometimes we call it a right Riemann sum. And we'll note that when the function is increasing, this is an overestimate. And when our function is decreasing, this is an underestimate. And you'll want to know that because they will often ask you that on the AP test. Good or no? Yeah, no, maybe, just no. Good, bad.
Great.
All right. In general, the left approximation and the right approximation are equally as horrible as each other. They're the worst two types of approximations that we're going to use. But the right rectangular approximation makes the algebra really, really nice and easy for when we want to convert this later on into an actual integral. So right Riemann approximation is actually exceptionally helpful. All right, what's the next one we could use to approximate it? Midpoint. A midpoint. So a midpoint rectangular approximation, which means we're just going to take each of these subintervals, find the midpoint of them, find the value of our function at that midpoint, and then draw a rectangle using that value. This should be a better approximation in general than both the left or the right approximation should be. Yeah. And whether the function is increasing or decreasing in this case isn't going to give us any information about whether or not this is an underestimate or an overestimate. Good or no?
Great.
Great. All right. Cool. Any questions or issues with that? All right. Let's then take those methods and see if we can approximate the area underneath the curve f of x equals x squared from 0 to 3. We'll use a left, a right, and a midpoint rectangular approximation. We're going to divide each one up into 3 subintervals. So just real quickly, I'll give you guys a minute or so here to see on your own if you can correctly do this, and then we'll do them quickly together after that just to make sure that everybody did it correctly. So I'll give you 2 or 3 minutes here to take care of that. Sound good? Either way, ready, go, do it now. You guys finish that or no?
Yeah.
All right. So let's see here. Sorry, computer's having issues there. Okay, so our left rectangular approximation, we're going to start by marking off 1, 2, and 3 as our subintervals, and our first subinterval will be from 0 to 1. The y value of our function at 0 is 0. So that's a height of 0 for the rectangle and a width of 1. Plus the next one will have a height of 1 squared, or 1, times a width of 1. Plus the next one will have a height of 4 times a width of 1, which should give us in total 5. If we were to do a right approximation, first one should start all the way up here at 9, and we should get this nice rectangle here, which has a width of 1 and a height of 9. And then the next one should be a width of 1 and a height of 4. And the next one should be a width of 1 and a height of 1. Giving us a total of 14. Good or no?
Yeah.
Wonderful. All right. So then from there, we want to do the midpoint one. So our midpoint is going to look a little bit different. Our midpoint between 0 and 1, it should be a half. And so the height of x squared at a half is 1/4 times the width is 1 for the rectangle. And then the next one at 3 halves in here, when we square that, 3 halves squared ought to be 9/4 times 1. And then at 5 halves in between here, it ought to be 25/4 times 1. And adding all of those together ought to give us 35/4. Or I guess what, 8.75? Not about 8.75, but exactly 8.75. Yeah or no?
Indeed.
Yeah, great. Okay, cool. Everybody did that okay, felt okay about that. No issues with that.
Yep.
All right, cool. Great. All right, so last method for approximating that we need to be worried about is called the trapezoidal rule. So our trapezoidal rule for approximating just means that rather than using these rectangles to approximate the area under the curve, we're going to draw trapezoids. So at each of the, and this one ends up looking a little weird, we'll draw this one differently, but they're not going to have you approximate something that crosses through the x-axis using the trapezoidal rule. We will connect the heights at each of the endpoints to make a bunch of little trapezoids standing not on their bases, but standing on one of the other ends of them. And so our trapezoidal rule, which is generally more accurate than the midpoint rectangular and definitely more accurate than the left and the right rectangular approximations, can be found by just finding the area of each of those trapezoids. So suppose I have, let's say, this trapezoid right here. Well, the area of that trapezoid is base 1, so the height at the first part of the subinterval, right? Base 1 plus base 2, the height of the second part of the subinterval, divided by 2, so the average of the bases for the area of a triangle, I mean a trapezoid, times the height or the width, the length of that subinterval itself. So that's h, right? H is that, times y0 plus y1, or y1 plus y2, or yn minus 1 plus y sub n, divided by 2. Right? That's where this formula comes from. It's the height times the addition of the two bases divided by 2, or the average of the two bases. Everybody good with that being our approximation? So this can be used anytime you're asked to use a trapezoidal rule. And if the subintervals are unequal, your h values will all be different, or they could be different. Sometimes that's the case. Sometimes the h values will be the same, and sometimes the h values will be different. So if the subintervals are of different lengths, you have to just separately find the area of each trapezoid. If they all have the same height, what could we do?
Factor it out.
Factor out the h, and in addition to that, we could also factor out what?
The halves.
Half, right? So if all the subintervals are equal, this will equal h over 2 times y0 plus y1 plus another y1, so plus 2y1, plus y2 plus another y2, so plus 2y2, and so on until you get to 2y sub n minus 1s, but then at the end we only have just one single y sub n. Right, so we use the first height, or the first base once, we use the last base once, and we use every other base twice, once for the trapezoid before it and once for the trapezoid after it. So this is if we have equal subintervals. Equal subintervals, h over 2, y0 plus 2y1 plus 2y2, and so on until you get to y sub n. Unequal subintervals, you have to do each one separately and do all the calculations. And we will note that h, if these are equal subintervals, is always equal to the length of the entire interval from a to b, so b minus a, divided by the number of subintervals, which is always n. So h is always b minus a over n. Everybody good there or no?
I have a somewhat unrelated question. I noticed that sometimes you use brackets and sometimes you use parentheses. for certain things.
Like in
And
terms of like
I don't know
these
if I
are
was
brackets rather than parentheses.
I don't know if I was ever taught like the conventions for that, but I'm pretty sure I wasn't. So like, where do you use certain ones? Just so
I
that
mean,
know.
if we're talking about intervals, I think you know, right? Parentheses and brackets for intervals of numbers. You're good there. Or no?
What do you mean for intervals? Oh yeah. For intervals, I know like closed
Yeah,
or open.
Open
But,
and
like,
closed.
for
Okay. Other than
expression,
that, it doesn't matter at all.
it just doesn't. Okay.
Generally, I mean, generally you start with parentheses, and then if you have something outside of the parentheses that is also in some sort of parentheses, then you would use brackets after that. And then if there's something outside of that, you would use braces outside of that. But it doesn't matter at all. I mean, me putting brackets here, parentheses here, braces there, it's all the same. Generally, if I have like some giant thing, I just put it all in brackets rather than a parenthesis, but it doesn't matter whatsoever.
Okay. I guess it just like varies based on style.
Yeah, pretty much. I mean, generally everybody uses parentheses for everything unless they have multiple things and then they put it in brackets. But sometimes I, like in this case, just happen to do brackets because, you know, maybe because I had a fraction out in front, it made me feel like a bracket looked better there. I don't know. No difference.
Cool. Thank you.
Yep. All right, so here is our trapezoidal rule. This is all the stuff I just wrote on the previous page because apparently I forgot I had it all written here. So we just did the work on the other page. We have our trapezoidal approximation, T, or whatever you want to call it, H over 2, and then Y naught, 2Y1, 2Y2, so on, so on, so on. Good? And you can note that this is always an equivalent value to taking the average of the right and the left endpoint rectangular approximations. So let's have you do one of these. Let's have you use the trapezoidal rule to approximate this integral, the integral from 1 to 2 of x squared with n equal to 4. Oh, that's unpleasant. Maybe I should make that a different upper limit. What do you guys think? Should we make that a different upper limit to make your arithmetic easier? Take that 1 to 5. Just for the sake of your arithmetic being easier. Because I'm so kind and benevolent. Ready, go. All right, how'd that go?
Pretty great.
Great. So H, which is B minus A over N, ought to be 5 minus 1 over 4, or just 1. So this should be H over 2 times the first Y value, which is 1 squared, plus the plus the second Y value times 2 squared, so 2 times 2 squared, plus 2 times the next Y value, 3 squared, plus 2 times the next Y value, 4 squared, plus the last Y value, 5 squared. Notice how I have parentheses inside of here and brackets on the outside. Very fancy. And so when we put all that together, what does that all come out to be?
42.
How much?
42.
42? Does that sound good to everybody?
Yes.
Let's see, 57, 50. Yeah, you all agree with that? 42, sure.
Yeah.
Cool. Everyone's good, no questions, no issues. Everyone feels all right about the trapezoidal rule? All right, tonight I will give you an assignment with some rectangular approximations and some trapezoidal approximations to do. Some of them I think are on charts and some of them are not on charts. So if you have trouble with the ones with charts, we're not going to do any of those right now. The ones with the charts, you just need to find the values from the table. So hopefully that'll be easy enough when you get that assignment tonight. All right. So what we are going to do now then is we're going to develop the idea of what an integral really is and a way to find the exact area underneath any curve that we want to. And as we mentioned a little bit ago, the way to make this the way to make this approximation more accurate is if we just create more and more and more subintervals. And if we could have an infinite number of subintervals, and we could sum them all together, that would tell us then that we have the exact area underneath the curve, but only if we have an infinite number of subintervals, which is theoretically impossible to do. So what we do then is we take our partition, this interval of our function from a to b, we divide it into our different subintervals. And what I did here is I labeled some random one the kth subinterval right here, right, from x sub k minus 1 to x sub k. So that's the kth subinterval. It has a length of delta x sub k, and its y values are, y of k minus 1 and y of k, or y sub k. And if we were to draw the rectangle, and let's do it, I'm going to use a right rectangle here, not that it really matters. I'm going to use a right rectangle here. And if I wanted to write out the area of that, its area would just be the length times the height, right? And if we were doing this, I think I wrote a midpoint one in there, didn't I? So let's do it's going to look about the same. But suppose we did a midpoint one, with the midpoint being C. The height of it would be f of c sub k, if this is the midpoint at c sub k. F of c sub k would be the height, the value of the function, and the width would be the delta x in the kth subinterval, delta x sub k. Where k is just like a numeric thing, like this is k equals 0, k equals 1, k equals 2. This is the kth. This is the first, k equals 1 subinterval. This is the second, k equals 2 subinterval. This is the third. This is the kth subinterval. And so the area of this specific rectangle is just x sub k, or delta x sub k, times f of c sub k. Right here. This is just the area of that arbitrary rectangle. I could have chosen this rectangle with a midpoint of c sub k, or this one, or any of them. And if we were to sum all of them together, that's what we call the Riemann sum. And so what we want to do is we want to take that sum and we want to shrink down the intervals so that in the case of this, where they're not all equal subintervals, so that the largest subinterval is approaching 0. If we can make the largest subinterval approach a length of 0, then all the other ones that are smaller than it should also be approaching 0. True? Yes, no, maybe?
I assume so, since you told me.
Nah, I mean, if I shrink everything in here down at the same rate and make more and more subintervals by making the largest subinterval get very close to 0, if all the other ones that are smaller than that were shrinking at the same rate, they should also be approaching 0. I think that, hopefully that makes sense. Not just that I told you that it's true, but hopefully it makes sense. And so if I were to do that, we could then sum them all together by using a limit, right? And so what we've got here is that the limit as the norm of the partition, that's what this double bar with a P is, and the norm of the partition is just the largest subinterval that we have. So if we take the limit of the sum of all of the areas of all of the rectangles within there, that's what we call our integral. So the limit as the norm of the partition approaches 0 of the sum of all of them. And that's how we get around having an infinite number of them, having an infinite number of subintervals. We can't sum them all together unless we do it with a limit. And so this is kind of an irritating looking notation, obviously, for our integral. And it'd be a lot nicer if we had equal subintervals. And if we had equal subintervals, rather than worrying about one that was the largest subinterval, the norm of the partition, we could just say, let's make the number of them approach infinity. And then that would get rid of that extra variable in there of the norm of the partition, this capital P with the double bars. And we could just say the limit as n approaches infinity. So the limit as the number of subintervals approaches infinity of the sum of the areas of each of the rectangles that we've drawn in there. And our delta x value here, or delta x value, is no longer a delta x of k for the specific interval we're in, but it's just a delta x in general because all of them have the same length. And they all have a length of that h from the trapezoidal sum of b minus a over n. That's the whole idea behind integrals. We spent like, I don't know, those of you in my class last year, like 2 days talking about all of this that we've now done in 10 minutes. That ring a bell a little bit? Take your partition, make the number of subintervals infinity, and then sum the areas of each of them together using a limit, because you can't do it without a limit if we're summing together an infinite number of things. Good or no?
Yeah, that makes sense.
Everybody good? Any questions on that? That's the whole basis for integrals. So I want to make sure you get that. Remembering that K is just a labeling mechanism. The first height, the second height when K is 2, the third height when K is 3, and so on. Okay. All right, cool. So this is the best notation we've got for our integral at the moment. And we can say that that's the same as writing it in this notation that everybody's used to, which is called Leibniz's notation. This here is Newton's notation, and Newton first off did these integrals. This one is Leibniz's notation, the one that we traditionally use because it's a lot simpler. So the big extended out S is basically, summation, adding together the heights times the widths of each of our rectangles for our function from A to B. Same concept, same idea. The little squiggly S is our integral sign, right? And we go from A to B of the areas of each of our rectangles. I don't know why I said triangles. I must have been thinking about something else. I have no clue what. Good or no? So next very important thing we need to be able to do is we need to be able to go back and forth between these two notations relatively effortlessly, because you will be asked to go between them on the AP test almost for sure this year, assuming it is an in-person test, but who knows? It's still going to be that way. We've got 5 months still till that test, so we'll see. So first off, to go from this limit notation into an integral notation is pretty straightforward. Should be pretty easy. We're going to take an interval from -1 to 3, and we're going to partition it into intervals of equal length. And we're going to have m sub k be the midpoint of the kth subinterval, and we want to write this limit. The limit as n approaches infinity of the sum from the first rectangle to the nth rectangle of this. This is the height of each of our function, or the height of our function, height of our rectangle, times the width of our rectangle. And so all we have to do is say this is an integral of 3x squared minus 2x plus 5 dx, where the dx really just represents the infinitesimally small thickness of each of these rectangles. And we'll integrate from -1 to 3, which we'll talk about how to do in a little while, even though most of you probably recall how to do that, I hope. And this would be how we would convert this limit into this notation. Good or no?
Good.
Cool. All right. Now, the more difficult part of this that we'll have to spend a little more time on is when I give you the integral, but they say to write it in a limit notation. And so we're going to have to think back about how we do this. So first off, I'm going to draw out the function 3x because I think that will help us here as we begin. Here's y equals 3x. And we are integrating from 0 to 2. And if I were to draw arbitrarily in here some rectangles, and I'm going to draw them as right rectangular approximations. It doesn't matter how many I have. I've got, it's like 5 of them, and we're going to say that each of those is of an equal length. So anytime we try to convert an integral into Newton's notation for the integrals, one second. Okay, sorry about that. My kid got a math test, so they're allowed to use notes on their test because, you know, how else can you stop them from using notes? So he was grabbing all his notes off the table. Hopefully he doesn't do poorly. What now? Okay, sorry about that again. All right. So every time we do this, we're going to start off with a limit as n approaches infinity. So it's a limit as the number of subintervals approaches infinity of the sum from k equals 1 to n of, inside of here we need an area. So we need a height of our rectangles, and we need a width. And our delta x is always going to be our width. And the delta x is always equal to what?
B minus A over N.
Delta x is always b minus a over n, which in this case is 2 minus 0 over n, or just 2 over n. So our delta x is 2 over n. But then we also need an f of x sub k, right? And so we need to figure out what x sub k is. So x sub k, we'll first figure out what x sub 1 is. So for our first one, how far over do we go to get the height of this rectangle?
Isn't it plus n? Or wait, no, just one of those intervals.
Right. It's just 2 over n, right? What about for the second one? How far over do we go to get the height? We go over 2 of those intervals, right? We go over 2 over n times 2. And x sub 3 would be 2 over n times 3. What do you think x sub k would be? It ought to still be 2 over n times k, or 2k over n. All right, so x sub k is 2k over n. So this will become a limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k. So that'd be 3 times 2k over n times our delta x, which is 2 over n. Good or no? Which will become a limit as n approaches infinity of a sum from k equals 1 to n of, if we multiply all that out, 12k over n squared. And we should, with any luck, I hope you remember what the sum, I'm going to put this on a new page here, the sum from k equals 1 to n of k is? What does that equal?
Isn't it like 2n minus or 2 times n minus 1 over 2 or something?
Nope.
Or is it n minus 1 over 2? Something like that.
N times n plus 1 over 2. Now remember, what does this even mean? This is like adding 1 plus 2 plus 3 plus 4 all the way up to n. Right? This is equal to n times n plus 1 over 2. And this is just a formula that you should know. Right? You should already know that formula. The sum from k equals 1 to n of k is n times n plus 1 over 2. Reason being, you can figure it out really easily. Make 2 of these. Just do 1 backwards. And when I add the first one together, I get n plus 1. I add the second ones together, I get another n plus 1. And the next one, I get another n plus 1. And so on. I get a bunch of n plus 1s. How many n plus 1s did I get? I have 1, 2, 3, 4, 5, n plus 1s, right? This is n times n plus 1. And in order to get just one sum from 1 to n, I got to divide by 2. N times n plus 1 over 2. Good or no? Good or not good? Anybody still out there?
Yes, I'm good.
All right, so the k gets replaced when I do the summation with n times n plus 1 over 2. The 12 over n squared is just a constant within the summation. So this now becomes a limit as n approaches infinity of 12 times n plus 1 over 2n squared. And now it's just a limit to solve. This becomes the limit as n approaches infinity of 12n squared plus 12n over 2n squared, which if you find that limit, what does that limit come out to be?
Six.
Should come out to
Maybe?
be 6.
Okay.
Yep. Yeah, I mean, this is just 12n squared plus 12n over 2n squared. It's a rational function. The limit as n approaches infinity of this rational function. Since it's got the same degree in the numerator and denominator, you can just divide the leading coefficients, right? It's just 6. And hopefully you recall doing this last year if you were in my class, but yeah, convert it into your f of x sub k into 3 times 2k over n, take your delta x into 2 over n, and then evaluate the summation. Let's do another one. We have an integral from 1 to 4 of 4x dx. So this should become a limit as n approaches infinity of sum from k equals 1 to n. That's always the same. Of f of, so 4x sub k times delta x, with delta x equal to b minus a over n. And all we have to do is find x sub k. And so if we think about it, I'm going to draw this sketch again, and then from after this one, we're going to have a formula for this. We're doing 4x from 1 to 4. And I draw my rectangles in here. Doesn't matter how many I draw in. To get to the height of the first rectangle, that'd be right here, right? What's the x value right here? Well, it's however far over where our interval started, which is what? 1 unit between here and here. That's 1. So x sub 1 is 1. Plus, we also went over one of these subintervals, 3 over n. And x sub 2 would be 1 plus 3 over n plus another 3 over n. 3 over n times 2. And what's x sub 3 going to be? X sub 3 will be 1 plus 3 over n times 3. And what will x sub k be? 1 plus 3 over n times k, or 1 plus 3k over n. And so with any luck, we've now recognized, hopefully, that delta x is always b minus a over n, and that x sub k is always your lower limit, a, plus delta x times k. Okay. X sub k is always a plus delta xk. And that's what we had here, right? We had a, 0, plus delta x times k. So just 2 over n times the k, because a was 0. In this case, a is 1, so it's 1 plus delta x times k. Good or no?
Good.
All right. So we have a limit as n approaches infinity of a sum from k equals 1 to n of 4 times 1 plus 3k over n. Note the parentheses with the brackets outside of it, times delta x, which is 3 over n. And normally they won't ask you to go any farther than this, but it is possible that they might ask you to evaluate this out using this limit notation. So I think it's important that we practice it a little bit more. So first off, we'll have to distribute everything that's in there all through. So really what we're doing is we're multiplying 12 over n to both the things inside of the 1 plus 3k over n. So this is going to become a limit as n approaches infinity of a sum from k equals 1 to n of, let's see, it was 12 over n, right? 4 times 1 times 3 over n. And then 4 times 3k over n is 12k over n. So 36k over n squared. And we got to think again, what happens? What does it mean to sum together a bunch of 12 over n's from the first one to the nth one? How many 12 over n's do I get if I sum together from 1 to n of them? How many, if I sum together 1 to n of 12 over n's, how many 12 over n's is that from the first one to the nth one?
Is it 12 over n times n?
It is. That's how many n's I would be summing together, right? This means 12 over n plus 12 over n plus 12 over n times. So that'll be now a limit as n approaches infinity of 12 over n times n plus, and if I sum together a bunch of 36k over n squareds, that's 36 over n squared times k, which is n times n plus 1 over 2. Note this time I did parentheses and then parentheses again. Weird. All right. So now this is a limit as n approaches infinity of 12n over n plus 36n squared plus 36n over 2n squared. And this is just a limit of one rational function plus the limit of another rational function. First rational function should give us 12, and the second rational function should give us 18, which should total give us 30. Good or no?
Pretty cool.
Oh, you better believe it. It's pretty cool. All right, I know we're moving fast, but I'm really want to make sure we get through enough stuff that we get to cover everything that we need to in this class before the AP test. So, everyone okay with that or no?
Why didn't you apply the extra n to the 36k over n squared?
Oh, you're talking about when I went from here to here?
Oh, yeah.
Yeah, so I'm summing together 36 over n squared times k. So remember that k is each of these numbers increasing by 1. So this is like doing, let me put this on another page real quick. The sum from k equals 1 to n of 36k over n squared. That's like doing 36 over n squared plus 36 over n squared times 2 plus 36 over n squared times 3 all the way up to 36 over n squared times n. And if we combine all of those things together, if we're trying to add all those things together, they each have what in common? They have a 36 over n squared in common. So effectively, that's 36 over n squared times just 1 plus 2 plus 3 all the way up to n. And we already know what this is, right? This piece right here, this all comes down to be n times n plus 1 over 2. And so it's just 36 over n squared times n plus 1 over 2. Does that make sense?
Yeah.
Where alternatively, the other one, the limit, I don't need a limit on that, sorry. Oh, shoot. The summation from k equals 1 to n of, what was it, 12 over n? Yeah, 12 over n. Right, 12 over n, that's not over n, 12 over n is equal to, since there's no k's in here, I'm just adding together 12 over n itself a bunch of times. In fact, I'm doing this in times. So I'm putting in 12 over n's. Does that make sense? So this one is n 12 over n, which is 12 over n times n, or just 12, whereas this one is 36 over n squared k's, and k is n times n plus 1 over 2.
Yeah, gotcha.
Yeah, okay, cool. I just want to make sure, because yeah, I don't think many of you spent a lot of time doing summations in any of your previous classes, and we only did a little bit of it in our class last year, for those of you that were in my class last year. So important that we make sure we know what we're doing. All right, why don't you guys see if you can work through this one on your own. I will give you a minute or two here to see if you can figure this one out. Ready, go, using a limit and a summation.